Hello, and welcome to the Simulation Masterclass presented by ExtendSim. My name is Robin Clark, and I want to welcome Scott Weiss today from JMP. Scott Weiss will be presenting the JMP Visualization Showcase. Welcome, Scott.
Sounds great. Okay, so thank you, Robin, and I appreciate ExtendSim inviting JMP to share with you a little bit about visualization. We definitely have a lot of experience with a lot of our customers in working with large amounts of simulated data, and there's a real need to be able to visualize it, actually to kind of find the story in your data. And so what I want to do is share with you a little bit about some different facets of visualization that might be of big help to some of the work that you are personally doing. And I've got a few spots we can stop and ask questions, so if you have any questions, just key those over to Robin on your controls, and we'll answer those when we get a chance to take a break between sections. But I'd like to jump right in, pardon the pun there, and talk a little bit about this visualization. So first off, I'm sure not everybody on the call is familiar with JMP. JMP is a client exploratory analytic package from the SAS Institute. That's our parent company. We are created by one of SAS's co-founders, John Saul, who kind of saw the rise of the personal computer and the laptop and the power that engineers and analysts and scientists and anybody dealing with data would actually be able to bring to their data and want to really personalize and be able to drill down themselves and visualize themselves what's going on. So that's why we call ourselves exploratory software. So it's very dynamic, visual, powerful, and flexible. And literally, I'm a firm believer in just showing you what it can do. And here is just a whole bunch of data. This is actually one of my side projects. I have a farm and a winery over in the Philippines and also in Texas, but it's so easy for me to go and immediately start to look at things like what's going on with my quality and what's going on with my yield, and maybe I can look at those by fruit line type, and maybe I can do some different things with the graph and actually see where things are grouping and where the quality and the yield is the highest or the lowest. This is just me interacting with my data. So it's so easy to do to create these views and even create almost your own report, your own dashboard, so to say, of what you care about, from looking at more of a traditional bar and lines to actually one of these interactive contour maps, even being able to look at positional mapping. So this is just a very small subset of what we do, but it's all meant to be very interactive, and here I'm zooming in on one of my farms. So JMP is very dynamic and interactive. It's to get you out of the spreadsheet, just the table of data, and get you into very good visuals that help you see and help you understand your data. Now, much like ExtendSim, we have a couple of different flavors of our software, and there's one in particular called JMP Pro, which is very good for not only the exploratory analysis, but also for modeling. And modeling is very important to people doing simulation. So I'm definitely going to feature this product. So you'll see it says JMP Pro up here. That's the product I'm going to feature. And we'll show you a good case study of how this might work in practice. But to kind of cue this up, ask yourself these questions. You know, when you've gone and you've run a discrete event simulator and you've gotten a lot of data back, how do you look for patterns? Is it easy to explore? I mean, most of the time that's large amounts of data, a lot of rows, maybe a lot of columns. A lot of times there's some complex relationships you're trying to simulate there. How are you going to see those patterns? So that's the first thing. Am I really exploring with my data beyond just staring at a sea of numbers in a table? Second thing is, am I able to really find what's important? We kind of call this screening. Some people call it modeling. I, as an engineer, always refer to it as screening. But really, can I just find the vital few factors in the right ranges, right? The right settings, the right things to care about? Because I'm not just going to stop with one simulation. I'm not just going to, I want to actually optimize and get finer answers over time so I can really hone in on what's important so I can make decisions in my process or in my design. So that's the screening part. And last but not least, are you actually taking advantage of experimentation? So we can simulate on everything, but eventually we just need, I would rather simulate on only the most important, the vital things, and I would like to do it as efficiently as possible. Maybe it takes a lot of time to pull each simulated run. Maybe because of the variability involved, I have to pull a lot of, I have to spend a lot of time pulling the data just to generate one run. So can I get the most optimized results? And this chart we have at the bottom is one, I don't know if you've seen this before, they always called this the confusion matrix here, and this little parabola here, but I've got confusion on one side and information on the other. Of course, if I don't have a lot of information, I'm very confused. But there's a nice sweet spot here. If I get just the right amount of information, and they call that nirvana, you know, I like to be in that green area. I just want the right amount of information not to be confused, but there's a point at which I get too much information, there's too many numbers, and I start to get into this analysis paralysis. So the idea here is to be able to pair up JMP with tools like ExtendSim to get yourself in that green area, just the right information so we can understand what we need to do. So what I'd like to do in the next 40 minutes or so is walk you through a real example. I mean, we could show you features of the software, but that's going to bore you because there's so much it can do. Let's show you an example of actually pulling simulated software to solve a real problem. And here's a real problem. I have a supplier. They are making light plastic modules that are melted into a very, very fancy and expensive product. It's actually a white plastic deck chair. Now this is actually a pretty complex product, not because it costs a lot of money, because you can get them pretty cheap. But part of the problem is to make something white is actually difficult. Anybody that deals with plastics might tell you, hey, give me any color besides white. I used to work on computers. And there was a trend to make computers white there for a while, and everybody got off it. You know, now you see them, they're black, they're gray, they're silver. White's a hard color to get, and sometimes in making the color right, you affected the strength, the flowability of the plastic. And of course, you do that, you might end up like Goldilocks here and sitting in your nice white deck chair and having a break on you. So this could be a problem. Now, of course, we're going to simulate this, and there is a process. Here's the general process that we're looking at. And you see I have kind of a, I have to kind of prepare a filler prep, kind of mixing everything in a tank, and then I have to apply a polymerization process to it, and eventually I'm going to get these white plastic granulars that I'm going to melt down into my final product. And now, take a look here. I've got a lot of inputs and a lot of outputs I can simulate on. Everything here with the black dot, well, this is either a continuous or a categorical variable that I'm going to include in my simulation. Everything from amps to modifier percentages to fills to suppliers to shifts, a lot of things I can look at. And then I've got 3 outputs. Got a MFI, a CI, and a yield. Well, of course, there's competing outputs here. My yield, I love to be above 93%. My melt flow index, I love to be below 198. That, has to do with how well the thing flowed and molded and how strong it is. And then the color index, I love to be above 80, and kind of put that in. Does this chair actually look white, or is it purplish or gray, and people won't buy it? So we have some competing outputs. So not necessarily the most simple process to work on. Well, let's see what we can do about it. So I'm going to pull up the simulated data. Here I have 1,300 runs of simulated data. I can kind of see that down here at the bottom. Every row here is one piece of simulated data, and that goes across my outputs there, and then these are my input settings. I have quite a bit of information to go through. All right. So to make this easy, we're just going to look at 3 steps here: explore, screen, and experiment. On to explore. So explore, let's just visualize this data and understand what it looks like. Right off the bat, when I have my data, it's easy for me to go and say, let's take a look at my outputs here. Okay, I have my 3 outputs. What I'm going to do here is I'm going to actually stack them up. And you can see I get pictures and I get numbers. So with JMP, you will always get pictures next to the numbers. And that's real important. A lot of other statistical analysis software that you get your hands on, it is going to flood you with a lot of data, but it's hard to figure out what's going on. And the nice thing about this is it's pretty interactive. I can click on graphs. You see when I click on this bar here for yield, it kind of shows me where that information falls in melt flow index, which is kind of cool. If I go and I grab them all here, okay, these are some of the worst situations here of yield. So I can either singly collect them, or I can just kind of use this big kind of grabber square. Now this is some of my worst yield. I was below a lower spec. It was definitely not above 93%. I can look over here and see that 30% of my data is not below. And something I can do now under my distributions, I can go back and say, well, show me how that relates to the inputs. And I'll just look for the pictures here. Now let's slide across and take a look. Well, here's the slurry amp. Do you see a pattern? Do you see actually some, you see that when yield's low, my slurry amp's kind of low? But there's a little bit on the high side. Maybe there's a curved relationship going on there. Here's the modifier percentage. You can see when things are high, they tend to have bad yield. So you can just slide across and kind of explore your data this way and try to understand if there's a relationship just visually. So this is quite powerful. This is quite strong. Now another thing I can do besides just doing that, if I'm just going to take a look at yield up here, I'll minimize these type of things here. All right. I can as well, under this little hotspot, this is where we have all our options. I can say, well, what's this distribution look like? Is it normal? I click on a normal distribution. You see it gives me a reference distribution. It also starts to give me information here on what this would be if comparing this to a fitted normal distribution. I can right-click here. I can even do something like a goodness of fit test. And it's basically showing me if this number is very low. You can see when I hover over it here, it gives me a reading saying if this is small, it's indicating there's significance. And so basically, I was kind of hoping that number would be high. My probability would be high, saying it's no different than the normal, but it's saying 0.01. It's probably different than the normal distribution. And I can see one problem I've got is a lot of times with yield, if you get over 100% yield, or this factor of 1 here, I can't go higher than 1. But you see the distribution kind of assumes you can get higher than 1. So maybe this isn't the best fit. Maybe there's another distribution, a better fit. You can go to that continuous fit, and you can say all, and you can let JMP try to find something that is better. And here it's telling me I have a Johnson distribution that's better. I've got one that I'm just going to ask for because I'm told this works really good with yield data. This one's called a beta. And actually, I'm going to start over so this is really clear to us. All right. I'll force this across. And now I will just ask for this continuous fit, a beta distribution. Now look here at the reference line. The beta distribution's got a little hockey stick here. It kind of assumes you're going to kind of have a skewed distribution. And it's going to move between 0 and 1. Well, this is a percentage. This one works out real nice. And so this beta distribution here, and here's the information on that, is fitting very well. So these are good things to know. So this is the kind of stuff I can do, as well as I can further explore these relationships. I think we said slurry amp and modifier percentage looked a little suspicious. I'm just going to go into this graph builder. This is a drag and drop graph creator. It's very powerful. I'm just going to go ahead and throw yield in here. Notice it pulled in my spec limits. This information's actually, I was able to set it in the columns. Basically, it's metadata. It's pretty easy to enter in, or you could enter it in on the fly, but I already had it and said put it on a graph if it shows up. Now, I can take a look at some of these inputs, like slurry amp. I'm just going to dump it to the bottom, and modifier percentage. Now, instead of looking at points, maybe I'll look at lines. Up here at the top, this kind of controls what kind of graphs I look at. I can look for straight lines, I can look for fitted lines, curved lines, all kinds of graphics, bars, whatever type of information, type of graph I can dream up, I can just ask for on the fly up here. You can see here, I'm seeing that little curvy relationship here, where maybe there's a happy plateau in the middle of slurry amp. I can see modifier percentage, bigger is better. That's kind of interesting. Well, what does shift have to do with it? Maybe I can put shift as a grouping variable on the top, on the bottom. I can wrap by it. Maybe I can just overlay it and see if there's any difference I'm seeing by shift in respect to slurry amp and modifier percentage. Not seeing it there. Maybe I'll look at Corey the same way and see if they're holding the same relationship. So this is just very easy to go and visualize. So we can go here from the visualization all the way to being a little more formal and maybe asking for a formal fit, where I'll look at my yield against those two inputs. In fact, I'm going to throw in shift here as well. Nice thing on JMP, you see these little blue marks and the little red marks. JMP understands what kind of data you have, and it gets you into the right view. So when I click on this, it's trying to fit a line through these, which makes a lot of sense. I can sit there, fit a line through this one, see how good that fit is. Turn off the points. Not a very good fit. That That's my confidence that it's a great fit. It's only like 25% confidence here. I'd like that to be higher. Maybe I'll try fitting that more quadratic through it. Here's the linear fit. Here's the quadratic fit. It's getting better. So I can test these things out. I can look at points. This one here is probably going to look a lot better with the fitted line. There's a chance of fitting a line. Here I got all my data as well. Still a lot of information. I'll minimize those. This one right here, since I got a categorical input against yield, it's basically kind of going to let me do mean comparison. So I can sit there and say, you know what, check to see if the means are different. I will turn off the points on this one as well. It's giving me these comparison diamonds. I can see if these diamonds overlap or not. That's one way of doing it. I can ask for some comparison circles. This will allow me to click on the side here, and if, you know, B and C are different than A and D because these are red and that's gray, you can read them. Of course, I got all my information down here below with the numbers. So that's very interesting information, very easy to use. Okay. So this is just all kind of things I can do to look at what's going on. Even when I have a statistic or a test that's going to give me a sea of numbers. Like maybe I was really worried about possible correlations within the inputs. And I'll go in and maybe ask for a multivariate chart. And I'll look at all the inputs. And I'll say, okay, well, I get so many points, I can't even see the scatter matrix. I get a big bunch of numbers up here. Those aren't so interesting. But maybe I can ask for a color map on the correlations. And now I get something that I can easily go. I can hover over different squares here, and this is slurry amp times viscosity, and it's close to gray, which means there's almost no correlation in those inputs. Anything on the gray, there's no correlation. Versus something like slurry amp against slurry amp where there's perfect correlation. That's an example. So I always have pictures next to the numbers. And by the way, if I like anything that I have done, it is very easy to save it back to my data table or anywhere else for that matter. So if I really like the distribution work I did with those outputs, and there they are, at any time I can just save my work. I call it saving a script somewhere. I can save this back to a data table, for example. Now it's kept it with my data. I can right-click and run it. It's going to reproduce the view. And actually, you'll see that I'm going to use a couple of scripts that I've saved back to my notepad. And this is what I'm demoing off of today. It's kind of our blank notepad / slide deck. And this keeps me from having to copy and paste things in the PowerPoint or PDF. You know, now I can just kind of stay within JMP and actually move back and forth. So here is, so for example, there's that multivariate chart I saved. This one, you're seeing some darker colors because I included the outputs in the correlation of the outputs within each other. And now I can see something like melt flow index and yield have a negative correlation with each other. That's just an example, and I save this directly back to this little report. But right now, I've got kind of an idea of visually kind of what's important, but I would like to go and do something a little more formal. And I think, like Robin mentioned, I'd like to actually create a model, something, you know, formula that explains what's going on, and use that to maybe fine-tune what I want to do next. So I want to do some more simulation. Maybe I want to experiment into that simulation. And it's kind of the difference in looking in the rearview mirror, right, and just, you know, running a simulation, looking at the data and going out and saying, okay, I can make things better, let's just fix things, versus truly optimizing. And I know if I truly want to optimize, it's probably a series of studies, a series of simulations. a series of experiments that's going to let me fine-tune and hone in on the right answer. So to do this, let's go ahead and build a model. Now, I'm not going to show you every model we can do because it's so comprehensive, but I'm going to show you some nonlinear models, some linear models, just a couple that I think are used a lot that you might enjoy. And one thing that I did with this data is I've got 1,300 rows of data. I don't have to throw all of it into a model. If I throw all of it in a model, there's a chance I might overfit the model. Instead, I can ask JMP here to allow me to section it up a little bit to allow it to give me a better model and prevent this overfitting. And the modelers like to call this thing TVT, or train, validate, and test. And train basically is, this is just what's going into the model to make the model. You can see highlighted back to my data set when I click on that train. It's just these rows that are going to go in to make the model. There's a column here kind of telling me which ones are going in to make the model. What's validate mean? Well, validate means it'll help me, it's going to help that training data set tune. Basically, a lot of these processes, if you think of stepwise regressions or things like that, sometimes the model needs to know when to stop. Otherwise, it just mathematically does it, even if it's not very significant. And that's how you get overfitting. So tuning is actually going to help tell the model when to stop adding factors. And, you know, of course, you want to have as few factors as possible that explains the most. Test is just what it sounds like. Test is a holdout. And basically, another good practice is, I know if I throw all 1,300 pieces of data into modeling and tuning, what do I have left to say if it's any good? What if I hold out? What if I just send all the test data around the corner and not involve it in making the model, but later come back and apply that model and see how well it would have done against that holdout data, this test data. So you see, 25% of our data we withheld for testing, and the rest of it's making the model. 50% is going directly in the model, 25% is helping to tune it. So this is, you can do all kinds of scenarios, but this is very, very helpful. And I will show you why real quickly on our screening here. So the first thing I'm going to look at, the best nonlinear model I know to use is this partition. It's actually a decision tree. It's a very nonlinear way of coming at my models. It really finds relationships and curves and interactions without me asking for it. It's got a lot going for it. I'm going to put my yield up here. I'll put all my inputs in. All right. And that's all I'm going to do. And basically, all it does is it will look through all my data and it will say, is there a way I can break any of those columns of inputs into two groups? So that's why you're seeing cut point. And it'll try different cut points, but basically it says, can I split into two groups, and will that explain anything? And this is the R squared. And when I hit split once, well, 40% of all my data, the difference I'm seeing in yield, can be explained by this two-way split of slurry amp. And obviously when slurry amp's greater than 55.98, I get a mean of 0.95, but when it's lower, I get 0.86. So this is a different kind of modeling, and it's really cool. I can continue to split, and I get the next best split. I'm up to 55.7%, and you can see even if my slurry amp drops, if I can keep the modifier percentage low, at least I stand a chance of getting close to my lower spec of 93%. That's how the decision trees work. Very easy. Now, here's the problem. I'm splitting. You see this number going up? When do you stop? I mean, mathematically, I might run out of capability of splitting, but it's sure not going up very high. It's going up very incrementally. It went from 0.784 to 0.788. Look at a split history. This little graph, this is showing you the bang for the buck, and you see how it's leveled out. My first splits got me a lot of predictability, but then it's just kind of nuances. And by the way, it can split something more than once. You see here it went back to slurry amp and did another two-way split. So I'm not really getting great information here. Now here's the difference. If I go back, and I go back into the partition, and I recall it for this decision tree, but this time I put in the validation, take a look at this. Now it's got my segmenting of my data. It's got a go button, and when I hit the go button, it automatically stops. It stopped after 19 splits. You can see here, the blue line would have kept going on forever. That was the model, but the red line was the validated data, and basically it said, you know, right around here, this really started to level off. So this is probably the right amount of splits I get on my test, 73% predictability, not too bad. And I can even ask for a little report of just what's contributing. I'll put this bigger on your screen so I can see it split slurry amp 7 times, modifier percentage 6 times, Corey 4. So this is cool, but this is one tree. This is one big tree. I always liken this to Survivor, if you remember that show. You see, it kept dropping the person in the middle of the forest and following out with the camera, and sometimes he followed the river, sometimes he went over the mountain, but always they chose what they thought was the best path to get out of the wilderness. Well, the truth of the matter was, I could have done more than one tree. I could have asked for a forest of trees. And what this does is this does a different process, which basically says, you know what? Build up to 100 trees. Make sure you include at least 4 of the input columns in each tree, and make sure there's a minimum of 10 splits. So basically, build 100 small trees. What does this look like? 0.799. It looks better. What did it do? Look at these column contributions. It split everything because basically it randomized what went into each tree. So everybody got a chance to play in the single tree. If I compare them side by side, right, in the single tree, like XF didn't even get to play. XF didn't make it into that one big tree. But here XF got split 503 times. It didn't come out very important. Still slurry amp and modifier percentage. Look at ambient temperature. It's now in 3rd spot, explaining 4% of everything. This is kind of cool. So this bootstrap forest is really helpful. And this is really good on simulated data. So this is a good nonlinear modeling way of finding what's important. Now you might say, well, this is good, but also I like to do regressions. I like to do linear models. Sometimes that might fit my data better than using a tree. So I've got a whole platform, this fit model that lets me set these up. And we could put the yield up here as well as put on my inputs. Now when I add effects in, I'm going to add I'm going to ask for enough information to even look at curvature, look at response surface, because I need to look at main effects and interactions and curve terms. There's a lot of stuff here. I definitely want to use that validation. I don't want to overfit this. But if I come over here to the stepwise platform, this is cool. I can say, hey, computer, don't build a model and make me figure out what's important and strip it out. You do it for me. And that's all that's happening here. It's going to use that tuning set to create this model. See, there it goes. It's figuring out what's important. My test is 0.7899. Well, that's even the best yet, right? I'm going to make this model. I'm going to run the model. It's telling me, oh, might want to add in the pH effect because it probably showed up in an interaction. So I'll do that. I'll run it. Here we go. Here's graphics showing me how important by the big bars are the factors. There's the pH I added. It's not very important. See the small bar? But take a look at shift times pH is important. So when you combine it with shift, it did make a difference. All this is cool. These numbers are strong. But down here, I'll look at my factor profiling. This is a graphical way of looking at my data where I can move my little toggles here, and it will show me different settings, and it'll show me what my expected output will be. So here's that high point for slurry amp. But look at modifier percentage. If I move modifier percentage up, what's my yield prediction? 103%. Can you have over 100% yield? You can't. One of the problems here is this is assuming normality. We already looked at the distribution and know this is skewed data. That beta distribution fit better. So how I'm going to handle that is this time when I go back to the model and I set up my model, this time I'm going to ask for a generalized regression. The cool thing here is, look, now it lets me pick what distribution's important. The beta distribution was the one that looked the best when we checked it. Now when I run it, I've got all these regressions I can run. That forward select is the stepwise we just did. There's things like lasso, there's things like elastic nets. There's ways of running these. I'm going to click on my script because I ran a couple of them here. And so my stepwise regression is down to 0.73%. But that's using the right distribution. That's not going to let me over-predict. And I can move these tie bars back and I can see how it builds, and you see it's giving me kind of a look at where's the best spot to model. That's really cool. So that's kind of the forward select. Also, I have other methods. This one's a lasso. This one actually is like a stepwise, but it applies penalization properties when you build the stepwise, and it stands a chance of getting as good an answer as a stepwise regression, but doing it with less factors. And it handles complexity well. So a lot of people that simulate like to use things like the lasso, the elastic net, the ridge, these penalization properties when they do their regressions. You can see I got really good predictability. I can see what factors entered into the model when it said to stop. It's very interactive to look at. So the nice thing I can do, I can save these prediction formulas. And we did that, and we will compare them all. Now when I hit the comparison, here's all the ones for yield. Here was the partition, here's the bootstrap, and then here are the two regressions I ran. And here's a comparable R squared. This is basically, the closer to 1, the more predictable it is. And so this last one had the highest predictability and the lowest squared error. That's one way of looking at it. Other ways I can look at it is I'm going to look at the profiler. I'm going to do that one. Take a look at the profiler. Okay. So here's the profiler. If you look up here, you see this really steppy looking one on this first column. That one is the decision tree. Here's the bootstrap forest. It kind of curved it out. And then here are my two regressions. So I can look at these profilers and see how well I think they fit, as well as I can look at things like prediction versus residual kind of thing. So here my model line's kind of this line here, and how close the points fall on that line is how well things are predicting. And I can compare which model I think is doing the best job, is hugging that line closest. So we have all this information that I can use to do this comparison. Okay? And we also did this for melt flow index and color index. So moving on from the modeling part, I'm now ready to figure, I now have a very good model, a very good fit on what's important. Now I'd like to do another simulation, but I would like to experiment first. So that's kind of where I'm heading. Okay. So my takeaway on this part, bootstrap forest, those decision trees are very good for simulated data. That generalized regression platform is very good as well. And you can run a bunch and you can compare them and pick which one you like the best. So the profiler is where you want to end. And you can see, before I go and set up an experiment or a simulation, I would like the profiler. So here's the profiler for all the yield. Again, as I showed you, I can change the settings and I can see how they'll work. So the first one up here was the best model for yield. Here's the best model for melt flow index. Here is the best model for color index. Now some of these have obviously relationships, like here modifier percentage when it comes to melt flow index, definitely slurry amp for modifier and yield, but not so much color index. So you can use this alone to figure out which ones you really want to focus on. Here's one where I threw out the factors I didn't care about. So basically I decided slurry amps, modifier percentage, this XF, and this ambient temperature were the ones that most of them were worried about. Okay, now I have a bunch of controls. I don't have to do this manually. Right now I can play with them manually. I can see how they predict. But something I can do is turn on these desirability functions. What they do, you see they added a box over here on the side. If I take a look at what's going on there, basically it's showing me my specs. Here's a match target. Remember, I wanted to be kind of between 93% and 100% yield. So basically it's saying at 100% desirability, I want to be on target. Down here at the bottom, you might see, like for melt flow index, I just want it to be as low as possible. So at 100% goodness, I'm as low as possible. And color index was as high as possible. So you don't really have to pay attention to these lines. All I have to know is I can maximize the desirability. And after I give it a second, you can see it is going to go and do an optimization to get me the optimized settings. And remember, I've got 3 outputs, and it's trying to find the sweet spot in between those 3 outputs that's going to help me hit a target, minimize the other, maximize the other, even though some of them are, in some cases negatively correlated with each other. So here's the key settings. So I'll turn off desirability so we can look at them. Oops, a little too big, sorry. There we go. Here are the key settings. So if I really want to do well, slurry amp at 72, modifier percentage at 0.296, XF at 15, ambient temperature at 8. Oops, actually move that back to 15. There we go. Okay, now it's not so simple, right? And that's why we're doing simulation. That's why we allow things to vary. So of course, I just can't go to the floor and say, we're done, hit this. This is what the simulated results came off of the first time. We modeled it. This is all you need to do. What I'm going to say is, well, things will vary. And so you can add on just a little Monte Carlo simulator onto the profiler, and you can say, I want to randomize by some distribution what I expect slurry amp to do. You can play with the bars. You can type it in. You can set a ratio. You can do whatever you need to do. And the cool thing about this, if I take a look at this one here, you can see here that I can simulate. I can control how many runs I do. I run this little Monte Carlo simulation. I get a little control box. I can see what's happening. I can even simulate this to its own table. Here's all 5,000 runs of that simulation. Here's a little distribution. Now I can get an idea how much better the capability would be, where I need to go, what I need to do. Okay, this is invaluable information because playing with this kind of information with my profiler ultimately is going to help me come up with the right settings for a DOE. So from this profiler, I can actually sit here now and I can come up with the right factor ranges that I want to hone in on. It might be ones I've already got because like slurry amp, there was a high point, there was a plateau. It might be actually experimenting and simulating on a setting that was beyond the range of what I had done before, like modifier percentage all the way down to 0.3, so getting lower on modifier percentage. Okay, so here's an example where for the first 4 factors, they use that profiler to set the range. And down here, they used it down here as well. They included 2 more factors that were even part of the simulation that they decided were important. So the net is I have new factors of low and high settings. I've got, and of course, I've got my same outputs. Now what I can do is I can go into an experimentation, and I can sit right now and say, you know what, pick a traditional design like a screening design or a full factorial design, or my favorite is custom design platform. This one kind of asks you first, what do you care about? I can load in, I can type these in, or I can load in these factors. So here I loaded in these factors, and there's my 6 continuous factors that I put in. So I don't need that one anymore. I'm going to read in these outputs as well. So I'll just load the responses. Don't need that one anymore. And now it's in here. And why I like this platform is it basically will allow me to specify what I care about. Like I know these things might interact. I know that slurry amp modifier percentage might have curvature. So here are all the factors I'd like to see. Now, down here at the bottom, you see this 24 to 28? Those are the designs available to me. Instead of using a traditional design, the custom designer will surface them all, but it'll give you a range, and it'll let you build what you care about. If I can only afford to do 26 simulated runs, I can type that in. And when I say make the design, this will go and make the design that I can go and apply the simulation to. And it will try to do it as efficiently and in as balanced a way as possible. So here I see the recipe card for all 26 designs. This design evaluation at the bottom lets me see how powerful the design is. So I can see what my confidence is. I can sit there and look at whether I might have too few runs and I might have some confounding or some correlation in the design. So I have ways of evaluating the design. But when I'm ready to go, I make the table and we go and we run it. And I go out and I do the simulation, and I can pull this back into the ExtendSim world, and I can go and we can run that ExtendSim, and I can go fill in these values to then analyze. So this is a way of setting up designs. We have designs that allow you to do them traditionally with a lot of confidence and a lot of robustness. We even have faster designs available to you on the DOE side. So a good place to start is that custom design. Here's the one that I ran. It looks like I asked for 34 runs based on what I wanted to see. We got that one set up. There's a definitive screening design. This one can get me that information in maybe 13 runs, but I'll lose a little bit of power. So this is an example of doing a screening design. This is one I set up where I just looked at 13, but it showed me how I could vary my terms. And if I take a look at one of these results, so here's, I did the screening design, and you can see here's my 13 runs, and what's in orange? That's what got simulated. That's what got simulated. Now, after you get the results, the modeling is exactly the same. Here I went and I did, in this case, I did a stepwise regression, and I ended up with a profiler and could judge how predictable the model is. In fact, we did this for all 3 outputs. And then here's the profiler for all 3 outputs. And now I can do the same thing. We can go back to the game of maximizing the desirability to see the best fit. simulating with the Monte Carlo simulation to get variation and further explore this space. So that's where I want to end up with. I want to get that back with a model, but this one was generated from a DOE that went into the simulator. Now, this was real data. This was a real situation. They took a sample from there before they ran that DOE simulation, and then they took 50 random observations after. Here's what their before and after looks like. And this is just looking at it in the graph builder. But is yield consistent, less variable, and high? Is no flow index low and predictable and not as variable? And is color index above my lower mark? Right. And so a lot of ways of looking at it, even control charts and doing all kinds of process capability, all kinds of ways of visually showing it. And I could copy paste this as a picture in anything, again, save it out as a PowerPoint, save it as a PDF, take these visualizations everywhere, because R squared might be good for me to mention to you, probabilities might be good for me to mention to you, but nothing beats a good picture for my boss. All right. And of course, I was amazed I could find a nice picture of someone sitting in a sunset, but sitting in a very cheap white deck chair. But I imagine now that's Goldilocks. Now she's sitting on her chair and it won't break, and she took it to the beach, which is a good place to be, right? Okay. So we just explored visually with that first round of simulated data that we had laying around. We used some modeling to figure out what were the important factors. The profiler really, really helped us hone in on the right ranges to do the next experimentation on, and that helped us set up the next simulation where we did it through a design experiment, and we're able to then get back into the profiler to find the optimized results that drove a happy outcome. So any questions on that last piece?
Whenever you set up the number of replications that you was going to push into the DOE, there was one scenario where you had more runs than what it suggested you needed. Since we're using simulation, we can do more than what the DOE suggests. Will it replicate any of the above runs, or will it come up with new variations within them?
You have complete control. Let's make this more interesting. So here I've got a response, and I've got, several continuous factors, even a categorical 3-level factor. I say continue, and maybe I think these things might be interacting. So it's telling me I can do from 13 to 18 runs. You're saying I'm simulating, and I'd like to add replicate runs. I'd like to add center points. You could type them in right here. You could say I would like to do 25 runs. It will go and it will make a design for 25. So again, based on the cost of running your simulation, based on time is money, right? A lot of times based on the time. If you tell me it takes a whole day to make one simulated run, wow, you probably want to use the least possible and find the most efficient. But here, this will generate a 25-run design. And of course, the more you take, up to a certain point, the more power you're going to have in that design. But there is a certain point at which it falls off, where, just more is not necessarily better. So you'll get a chance to really play with that and explore it and see how good, how powerful will this be. And at this level of significance, if I said this was an important factor, how much confidence do I have in X1 being the important factor, irrespective of the others? You see, things here are very powerful and very high. Just an example. So you have that capability. That's why that custom designer is nice, because it puts you in control. It's not you fitting a design to the back of a table, which is kind of how most other people treat designs. You know, go out, go do a 3-run to the, a 2 to the 3rd factorial design. Oh, I got 4 factors. Tough. Drop 1 and do 3 factors. That's what the design says. We do it the other way. We let you put in what you care about.
So I have one question here that says, if you can afford more replication or more time to simulate it, would it be better to add replicates, or would it be better to increase the number to 25?
A lot depends on your process that you're simulating. You know, if it's a very unstable process, I've had some customers say replicates are very important. In fact, when they experiment, they automatically build in like 2 or 3 replicates. So it's basically replicating the experiment 3 times. In the processes I was in, I didn't have that problem, and I didn't like replication. I would much rather add runs to an existing experiment, like add some runs at a center point, or run the experiment and then augment the experiment with some additional runs where I care about. But of course, I was doing live experimentation. Even when I did simulation, my simulations were expensive because I had to make a lot of mock-ups and prototypes and do a lot of testing in labs, and it was all money. So if I can get there in a smaller experimental number of runs, I saved a lot of money. So it depends on the situation you're in. But just kind of knowing your process, does it make sense to replicate, or does it make sense to add runs? My guess is most chance you'll get more bang for the buck from just adding runs, having a bigger experiment than replicating. But if you really need to replicate, it can be very important.
Okay, and one other question, thoughts on space filling designs?
Yes, space filling design. So very popular in simulation is really, there's a couple of DOE design types that are popular. Space filling designs, think about having a cube. You know, in the way mostly we experiment, we have low and high points, and maybe we test the center. But say you want to test all the space within that cube, even some points that might not be in the corners where the high and lows are, but not exactly in the center. They might be like a quarter of the way in. A space filling design would help you see those. And we have a little dialogue here that helps you build space filling designs. And there's a lot of different ways of doing it. Like here's a sphere, like getting optimal points within a cube, a Latin hypercube. So there's a lot of good designs here that help you do that. The other thing, and I didn't mention it, but it's new, is actually covering arrays. We're one of the only pieces of software that actually offers space filling, covering arrays, and custom designs, and definitive screening designs. They're very advanced. And the covering array allows you to make designs where you cover as many combinations of things as possible in the shortest amount of runs. And some of my customers, they might be like doing software simulation, and they might have, they might be testing, loads on a phone, and they have different programs, and there's all these different use cases, but they have to make sure they cover all combinations. This is a way for you to make those designs. So lots you can do. If you want to see this in more detail, and I want to say this before we finish, and I apologize for going just a little bit over today, but check out jump.com. We have a lot of webinar and free instructional learning videos and material. And if you want to learn more about space filling designs, we got a free webinar on that where you can get a good primer for it. And, even links where you can go and try it out with your simulated data. And a lot of links to white papers and books where you can read more about this. Things like DOE, space filling designs, even the modeling and exploration that you saw me doing earlier. So whatever your speed is, whatever you think can help you with your, get off the sea of numbers and actually start to visualize, model, even experiment in your simulation, you should be able to go and find some good references to it.
Okay, that was great. We are out of time now, so we need to wrap it up. I want to thank you, Scott, for taking the time to show us JMP and how it could be useful in simulation projects. Have a good day, everyone.